All right, so we're just going to keep going with rotating coordinate systems. We've been working on this example where we have this rotating piece connected to a disk. This is rotating at 5 radians per second. This is rotating, I think it was this direction, is that right? At 10? And we're interested in what's happening with this point P. And the radius of this disk is 0.6 meters. We did it with the coordinate system fixed down here. And now we're going to do it with the coordinate system fixed here. So with the new coordinate system, there we go. Notice that the origin is moving in a circular path. And so that means the origin's accelerating. And so the acceleration of P relative to the ground is equal to the acceleration of P relative to the origin plus the acceleration of the origin relative to the ground. The acceleration of the origin relative to the ground is a centripetal acceleration since this is moving with a constant angular velocity around that orange circle. And we did this last time. The acceleration of the origin relative to the ground was equal to negative 17.677500. Does it make sense? Hopefully it makes sense to you that that the acceleration of the origin only has an x component, because at this instant a vector going from the origin towards the center of the circle is in the negative x direction. And now we have to calculate the acceleration. So, okay, if you're working on a problem like this with 2 people, try to get them to let you do the acceleration of the origin relative to the ground, and they'll do the one with the rotational axes equation. Okay? It'll make them hate you when they figure out what you've done to them, but that's okay. You'll have more free time. So acceleration of P relative to the origin. Now that's the tricky one. And that's equal to the acceleration of P that's observed in the coordinate system plus capital omega dot cross P plus 2 times capital omega cross the observed velocity plus omega cross quantity omega cross P. And we figured out what most of these things are that we need. Capital omega the rate that these axes are changing orientation is connected to the rotation of the base of this shape. That's the 5 radians per second. That's in the negative y direction. So this is 0, negative 5, 0. It's a constant angular velocity, so omega dot is 0. The position vector is just to the point P from the origin in that coordinate system. So at this instant, that's equal to positive 0.4243, negative 0.4243, and then 0z. And let's go through the calculations of the observed values now. So in that coordinate system, the point P is moving in circular motion with a constant angular velocity about the vector 0.7071, 0.7071, 0. So it's in circular motion about this axis. Wait, did I draw that the right way? Is that the way we had it in the problem? Okay, so, oh, no, what am I thinking? No problem. Okay, so this is the axis of rotation, and you know that because of the right-hand rule. For a second, I did a mental left-hand rule, I guess, but the right-hand rule says the axis is that way. So our angular velocity is equal to 10 times 0.7071, 0.7071, 0, which is 7.071, 7.071, 0. There's no angular acceleration. And so the observed velocity is equal to omega cross r. So that's 7.071, 7.071, 0. Notice that just in this case, we have a circular motion that's we have a circular motion. The center of that circular motion is the origin. So this is just one instance. This isn't generally true, but where our vector is equal to our position vector. So r is equal to 0.4243, negative 0.4243, 0. And since it's tangent to the circle, that should be in the negative z direction, and you just get a value of 0, 0, negative 6. And then the acceleration observed is equal to alpha cross r, that goes away, plus omega cross quantity omega cross r. So that's 7.071, 7.071, 0. cross quantity 7.071, 7.0710 cross 0.4243, negative 0.4243, 0. And I think what we get here, that's just a centripetal acceleration. So it should be pointing. So it should be pointing towards the center of this circle, which has a negative x component and a positive y component, and we get a value of 42.43 negative, then positive 42.43, and then 0. And then we can plug everything into the equation. So the acceleration of p relative to the origin is equal to the observed acceleration I'm going to leave off the z components because now everything is just going to have why would I do that though? Why would I do that? Let's just write it all out. And then omega dot crossed with the position vector. Omega dot is equal to 0. We already established that here. Then we have 2 times omega, which is, what was that? 0, negative 5, 0. Crossed with the observed velocity vector, 0, 0, negative 6. Plus omega cross quantity omega cross p. So negative 42.43, positive 42.43, plus, what do you get here? That should be, I think, 60, 0, plus this term, I think you get negative 10.6075, 0. Anyone want to check that one for me? No thanks. Okay. Expression.
Was 6.9625.
Okay.
And
42.43. Okay, and then so the total acceleration of p is equal to 6.963, 42.43, plus what we got for the acceleration of the origin, negative 17.6775. And so what do you get for the total acceleration? Negative 10 point something. 145. 7145, and then 42.43. meters per second squared. If I remember it right, that is different than what we got the first. What is the first term the same?
Yeah.
But we didn't have something in the y.
Yeah, the y didn't cross out.
Okay. Does it seem totally ridiculous to do it again, the first way? Okay, let's do it again. I agree. For what? Okay, so let's call this coordinate system A and this coordinate system B. So we have an answer for it in coordinate system B. Let's go back and do it again in A. I like green for a coordinate system.
Yeah, but there's different coordinate systems. Maybe you should use different shades.
But that's why I use different letters. Okay. Well, when I take a class from you, I won't, and use different colors, I won't complain. Okay, so here's this configuration that you're quite familiar with now. That's going 5 radians per second. That's going 10 radians per second. And the coordinate system, which I choose to draw in green, is like that.
What was the answer that we got the first time?
I think we got no y component, but we got the same x component.
Looking back at it,
Mhm.
we had the y component, we just didn't put our final answer.
Oh,
If that's the mistake.
okay.
And they would be the same.
Okay. Let's do it again anyways. Why not?
You already drew the picture, it's too late now.
Exactly. I already switched my pen to green to draw the coordinate system. Okay, so this one, so is the origin accelerating? No. Are the axes rotating? Yes. So the acceleration of P is going to be equal to the acceleration of P observed plus omega dot cross position vector plus 2 times omega cross V observed plus omega cross quantity omega cross P. So what do we know? The P vector, we did this calculation before. I don't have it with me though. So what's that P vector? It's
One point
1.283.
1.1.
1.28.
There's no one. 0.28.
Oh, okay. For Z? Oh, there's no. Okay, yes, I got you. For Z? Yeah, exactly. Well, the good news is we know that that all our values are right. We just didn't enter the terms in, right? So we can use all our same values, think it back through, and we'll get the right answer. Okay, so what's omega? Capital omega? There is a 5. There is a plus or minus 5 somewhere. Thank you.
In the y component.
Okay, 0, negative 5, 0. Omega dot is 0. And we need the observed acceleration and observed velocity. So the velocity of p observed is equal to lowercase omega crossed with r. Lowercase omega is times the vector 0.7071, 0.70710. So that's positive 0.7071, positive 0.70710. Ah, yeah, thanks. Yeah. If we get it wrong this time, how many times are we going to keep redoing it? And the r vector is positive 0.4243, negative 0.4243, 0, and alpha is 0. So the velocity of p observed is equal to 7.071, 7.0710 crossed with 0.4243, negative 0.4243, 0. And if you take that cross product, what do you get? Oh yeah, 0, 0, negative 6. And then the observed acceleration is equal to alpha cross r. That goes away because there's no alpha. Plus 7.071, 7.0710 cross quantity 7.071, 7.0710 crossed with the r vector 0.4243, 0.4243. Thank you. And if you do that, you get negative 42.43, positive 42.430. And now we can plug all these in to get the acceleration of p. So it's equal to the observed acceleration plus capital omega dot cross p, and that goes away because there's no capital omega dot, plus 2 times 0, negative 5, 0, crossed with the position vector, 1.131, and then positive 0.283, 0, and then plus capital omega, 0, negative 5, 0, crossed with the quantity 0, negative 5, 0, crossed with the position vector, 1.131.283, 0. And I guess it sounds like what we forgot to do before was add in the, we just forgot to add this in before. Is that right? I'm important. You're all important. Factors. Components. Come on, components. You're all important.
No, that's in there.
We just didn't put it in the answer.
They just said, oh, well, that's
Yeah.
the action, just move on to the next one.
Yeah.
We finished everything, but then like just adding everything up was just the excellent.
Okay. Well, so now, anyways, now you believe me that this works. This method still works after all these years. So negative 10.7145. 42.43. Again, flicking our noses at the bean counters who care about significant figures. It works. I hope you all think this is cool, because, I mean, this is pretty cool, isn't it? Like, these coordinate systems spinning around or whatever are giving you this information, and we have a way to correct that information so that we can use Newton's laws with this stuff.
Not cool at all.
Again, when you teach dynamics, you can take, that can be your angle on it. But in this class, the official angle is it's pretty cool. Okay, so now we're going to keep rolling with this. So usually with these problems, our two different motions are going to be two rigid body motions, where one's riding on the back of the other one, right? And these rigid body motions are circular and spherical motions. That's just what rigid body motions do. And because of that, so in that case, most of the time, the velocity of the point observed is done as a circular motion, and the acceleration of the point observed comes from the watermelon equation. Doesn't have to be the case, though. So I'm going to do one now where that's not the case. Okay, so say that we have a camera that's rotating according to 0, 5t, 0. And this camera is observing the motion of a particle. So let's say we have a 0.3 kilogram particle. And it records, sees a motion that's defined by the position vector as a function of time is equal to the cosine of 2t negative 3 times the sine of t. What's the net force on the particle? Okay, so this would be common in any kind of like aerospace application. But do you? In space, possibly. So you have a camera, something observing a motion, and you'd love to have that camera mounted to an inertial, be an inertial coordinate system, but you just don't have that luxury all the time. Sometimes the only place you can mount the camera is on something that's spinning. And so that camera is watching the motion. Well, an example of that is, the way that we observe the motion of stars and planets and whatever, It'd be a lot easier to make sense of what's going on if we were standing on something fixed watching them, but we just don't have that luxury, So this is an example like that. So how do we go from what the information that this camera tells us to what's really going on so we can use Newton's laws? Okay. The camera's rotating. Let's assume the camera isn't accelerating also. I guess that was sort of implied here because I only talked about the rotation. And so the acceleration of this particle is equal to, so when it's two rigid body motions, I tend to write this as the observed acceleration and blah, 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 something cross the observed velocity. But remember, you can also think of this as the second derivative of the components of the position plus capital Omega dot cross P plus 2 times omega cross, and we'll write this as the first time derivatives of the position components. And then plus omega cross quantity, omega cross P. So remember, you can think of this equation in either of these two ways. The second derivatives and first and second time derivatives of the components of the position, that's just another way of saying that's what the coordinate system sees. Okay. So let's figure out what we have first. Our omega is equal to, what did I say? 0, 5t, 0. And therefore, our omega dot is just equal to 0, 5, 0. Our position vector is equal to, what was it, cosine of 2t, and then 3 times, was it negative? Negative 3 sine t, 0. And so the observed velocity, the time derivatives of the components, is just equal to negative 2 sine 2t, and then negative 3 cosine t, 0. Take another time derivative of each component. negative 4 cosine of 2t, positive 3 sine of t, 0. And so the acceleration of p is equal to negative 4 cosine of 2t, positive 3 sine of t, 0, plus 0, 5, 0, crossed with the position vector, plus 2 times omega crossed with the components dot, so negative 2 sine 2t, negative 3 cosine t, 0. Plus 0, 5t, 0, cross quantity 0, 5t, 0, crossed with cosine of 2t, negative 3 sine t, 0. Are we really going to multiply that all out? Yes. By the way, if you haven't ever noticed this before, I don't know about the other TI calculators, but if you have an 89, you can plug this in, like if you have a function for watermelon equation, or if you have a function for this rotational coordinate system equation, you can plug these in as variables, and it'll do all those cross products and keep the variables for you. 0, 0, negative 5 cosine of 2t. Plus 0, 0, positive 20 t sine of 2t. Plus 0, 5t, 0, crossed with this inside stuff is 0, 0, negative 5t cosine of 2t. And this one gives you negative 25 t squared cosine of 2t, 0, 0. So the acceleration of the particle is equal to negative 4, we can lump these together, so negative 4 minus 25t squared, all times the cosine of 2t, zero y, nope, there's a 3 sine t, y, and then for z, we have quantity, no we don't, we have -5 cosine of 2t plus 20t sine of 2t. So that's the acceleration. And then F net is just equal to 0.3 times the acceleration of the particle. So now we have a net force as a function of time teased out from the information we got from that rotating coordinate system. Yep?
So is that the frame of reference in which the camera is accelerating 5t?
Yes, so what that's saying is at every instant, the coordinate system is in a new location.
Right.
But this is the acceleration measured in a coordinate system that was inertial with that same orientation. You know what I mean? So like at time equals 1 second, the coordinate system's here.
Right.
And what you get from that function is the net force that would be measured in an inertial coordinate system at that orientation.
Okay.
And then at time equals 2 seconds, the coordinate system's here. And what that expression gives you is the net force that would be measured in an inertial coordinate system that's now at this orientation.
So the inertial coordinate system is shifting with time based off the rotation?
That's right. You can think of it as, yes. So if you, maybe a better way to think of it than so it's a little bit of a tricky distinction. So you're thinking like, wait, so now we're talking about an inertial coordinate system that's turning in time. Isn't that a rotating coordinate system? Think of it more as like there are an infinite number of coordinate systems, of inertial coordinate systems waiting out there for the rotating coordinate system to hit those marks. You know what I mean?
Yes.
And this function gives us one by one the net force that's measured in each of those infinite number of coordinate systems.
Okay.
Yes?
But the acceleration is that based on like a ground measurement then?
The acceleration, the corrected acceleration is what you would measure in a ground. Okay, so let me give you a. Okay, so say. Okay, it'll make more sense with an example. So let's put an example in here. So let's say t equals 1. Okay. So plug in, the acceleration of the particle is equal to, excuse me, -29 cosine of 2 radians, 3 sine of 1 radian, and then -5 cosine of 2 radians plus 20 sine of 2 radians. And F net F net is just equal to 0.3 times all this stuff, so 0.3 times blah, blah, blah. Okay. And so our coordinate system is our rotating coordinate system at this instant, say, is at this orientation. There's x, y, z. And it's spinning around the y-axis. Which way is it going? It's positive, right? So this coordinate system is spinning. At every time, it's in a different orientation. Okay? But this is the orientation when time is equal to 1. This, yeah, don't get thrown off by that. That was a typo. This is an inertial coordinate system. Aligned with the t equals 1 coordinate system. Okay? This function, this expression, gives f net in the black coordinate system. Okay. If we, so this coordinate system isn't moving at all. It just happens to be aligned with the rotating one at the instant we care about. If we cared about instant 3, this would be in a new orientation, and our value would give us the force net in a differently oriented fixed coordinate system. Does that help? Okay. All right, that's it.